Hello and welcome. In this video, I'm going to go over students' t-distribution, which is related to confidence intervals, or how we calculated confidence intervals before. At least that's how we're going to use it in this video. So let's what is this students' t-distribution, and when do we use it? When, maybe, and why? So let's quickly review confidence intervals. So confidence intervals we created by taking a sample mean and then adding plus or minus the z-score of aleph over 2. Now remember, aleph is the percent likely, is 1 minus your confidence value. That's what aleph is. And then that is multiplied by your sample mean over the square root of your sample size. Okay, so but there was one limitation here, and one of the limitations were that n had to be greater than 30. And this limitation came from the central limit theorem, because the central limit theorem itself says that you need a large enough sample size in order for your sample mean to be approximately normal. And well, not all the time do you have a sample mean of over 30, or not all the time you can get a sample mean of over 30, but we still want to measure our confidence, and we still want to have at least approximate distributions for a sample mean. So that's where students t comes in. So when to use number one is when n is less than 30. So there's another side effect to n is less than 30. Now, what I was saying before is that the sample mean will be, from the central limit theorem, it will be guaranteed to be approximately normal, but now we lose this as well. So we lose the fact that this is approximately normal. And so we need another condition before we use the students t, and that is that x is approximately normal distributed. So note, before we didn't need that because of the central limit theorem. We didn't care how x was distributed, because it would be its mean would be approximately normal distributed. But now its mean is not going to be approximately normal distributed unless x itself is normally distributed. Okay, and so this formula is going to change, but notice it's going to change very slightly. So this part, when we're constructing an interval using the students t, when we don't have 30 or more than 30 sample size, we're gonna, well, this is where the name t comes from, this little variable here. And then, well, a lot of times it's written like, so a lot of times it's written with this fancy little v, that's standing for degrees of freedom, but you could just replace that with n minus 1. So n minus 1 here, and this thing takes two variables, but the second variable, the second argument here is the same as up here. It's aleph over 2. All right, and then this, just like z, is a value that you find on a chart, and we'll take a look at how we do this in a minute. And then this part is exactly the same. Okay, there's a lot of stuff going on behind the scenes about where this comes from, but we don't need to worry about all that. All we need to worry about is how we find a confidence interval when we have a sample size less than 30. Okay, so let's do an example of that. Okay, so we have an experiment. We don't know. Well, we know there's only 10 examples. So we've measured. Sorry for the extremely general question here, but we just want to get straight to the data and how to construct the confidence interval. And the key things about that is that there's only 10 examples, so we don't 10 measurements. We don't have a large enough sample size. We have its mean. This is the mean of the sample. So this is x bar, and we have n. N is 10, and we have the standard deviation of the sample, s. And we're assuming, as I said, we have to assume that the data is normally distributed, and not just the normal, not just the mean, sample mean, but the data itself of the examples is normally distributed so that we can use the t-chart. And now we want to construct a 95% confidence interval. So let's take care of this first, because this isn't actually a variable in the equation there, but this is. So we have to do this very mini calculation here. 0.95 is 5%, or 0.05, which means aleph over 2, which is what we want in our equation, is 0.025. Okay, so we needed this value in the equation. We need this value, we need this value, and we need this value. Okay, so our confidence interval is x bar plus or minus t, and the first argument here is going to be, well, we didn't get the, so you could just do n minus 1. N minus 1, in the formula I wrote it with this fancy v for degrees of freedom, but in general you just take this value. Degrees of freedom is just n minus 1 is equal to n minus 1. So that means that we'll get a 9 here. And then what goes here is aleph over 2, which we calculated over there, times s. S is 9.69 over square root of n square root of 10. Okay, so this part is straightforward. This is just some calculator work here, but what is this t thing and why? Okay, we have variables in there, but what do we do with that? Okay, we go generally, well, you can use, there's obviously lots of different technology that can calculate for you, but good old-fashioned way is just to go to a table. So in fact, one such table is in the back of your book, the very back in the cover, and probably most stat books, there's a t table in the very back, and this is very similar to your z-score table. So if you're comfortable with your z-score table, you should be comfortable with this table, although there are some differences here. It's not as detailed as what values of z you can have, but and it also has this extra degrees of freedom variable. So remember, ours was 9, so what we'll do first is we'll look for the 9 on this chart. So 9, and we're going to be explicitly in this row, and then above is the aleph, well, the aleph of one tail, so that's aleph over 2, another way to say, and we had this value here. Okay, so let me take that. We have 2.26 approximately, so let me just write that out. T of 9 0.025 is approximately 2.26. Oh, so one value I forgot to put into the equation here, but there's no issue, is x bar. I have it right there. So let me this time put it in here. And okay, so I have all my values now. 2.26 times 9.69 over square root of 10. Equals, okay, and now it's just a calculator problem, so let's go to our calculators and after a little bit of calculator work, I get 8.91 plus or minus approximately 6.925, and that gives me an interval of 1.98 approximately to 15.8. So I have a 95% confidence that my actual mean is in this range. And that's a pretty, well, this This example is so general, I have no idea what that means. Could mean that I don't know much of anything, or it could mean that things are all good. But would depend on the specifics.